In that last example, we can see that some functions can be partially described by derivatives and integrals of other functions. So for example, here we have g of x can be described by this part here, which is 2 of x. This is just a regular x part. But then we have another part that can be described by the area under a curve. And this f of x can be some explicit function. So for example, we could have some function defined like this, or it could be defined as area under the graph. So in this case, being an integral, we can just look at it as some area under the graph. If they are geometric shapes, we can calculate those geometric shapes using just some formulas, or you may be given these areas as defined areas. So for example, in this case here, maybe you're told this area is exactly 2, this area has some exact value. So these are different ways that functions can be described. So that's one way. For number 2, you can see that we can have some function g is described by an integral, antiderivative function f, and embedded inside some other function. So it could be some combination of other functions. So when we differentiate something like this, we're going to end up, when we differentiate the antiderivative f, we get f. But while doing that, we have to be aware of the different rules that might exist. In this case, there is the quotient rule. We can also have functions described as embedded functions or composite functions, and here you would be expected to apply the chain rule. So if we have an embedded f of x or big F of x inside the log function, as we differentiate this, when we differentiate the inside, we need to apply chain rule. In this case, again, the big F could be differentiated into little f.